tree?
It is not.
I agree. It is not.
So they don't have to be a binary search tree?
It's not a binary search tree. It's a heap.
Well, that's harder.
Cool. First off, let's Arva just ask a good question. Is this a binary search tree?
Yeah.
If it were a binary search tree, where would one be?
At the very bottom.
All the way left. Right? So it's definitely not a binary search tree. Cool. So we want to find one. What would the runtime be in this scenario for finding one? Why O of n?
Because they're still really like, because it's not so there is no short.
Right. Where is one definitely going to be if this is a max heap? Sorry? I agree it's not on the top. It is going to be a leaf. Right? In a binary tree, how many leaves are there? What percentage of the nodes are leaves? Maybe like in general, like roughly what percentage of the nodes are leaves? About half, right? So in this scenario, we got 5 leaves, 4 parents, right? So we would have to look over about half the tree because we have to traverse every single leaf, right? So, whoops, what did I just do? Whatever. So, do we want to use a max heap? Certainly not. We're going to be using a min heap, but we'll get there. Cool. First off, let's talk about how heaps actually work. So heaps are typically organized using arrays. I realize that sounds counterintuitive, but generally speaking, that is because heaps are often used for heap sorting as well. So we're going to be treating them as arrays in this course. Additionally, you need to be able to quickly find a parent. Right, so in our previous tree node class, we'd have to add a third node like we did on that one test question. So look at this thing, right? Familiarize yourselves with this, shall we say, way of describing this same heap here, right? Get up to speed in your mind that these two are the same thing. Right, so in general, our root's going to be here, right? Its kids are 80 and 85, right? 80's kids are 17 and 30, right? 17's kids, so 17 is at index 4, so its kids are at index 8 and 9, right? So you can see it's basically 2k and 2k plus 1. Yes, ma'am?
So, wait, why is int 0 blank?
Why is int 0 blank? Good question. I don't have a great answer to that. I just decided to make it that way. I guess it's so that this formula will work. But I suppose I could have just picked a different formula. I don't have a good answer to that.
Okay.
Yeah, good question. Yes, ma'am?
If one of the, for example, the left one only has for index 4 is null, so it doesn't have a child, then would you just put null in that spot anyway?
Good question. So let's go down to this nice question right here. Why must a heap be a complete binary tree? Talk to your neighbor.
Or you can put a note
Does anyone want to take a stab at explaining that?
Because if, let's say there's an only child,
Yep.
the 2k and 2k plus 1 wouldn't work, so all of the nodes to the right of that would be shifted down.
Totally. Right. Take maybe 2 minutes. Go through exercises on the front and the back. So numbers 1 and 2. Actually, maybe this will be like a 4-minute thing. We'll see. On number 2, don't draw it as a tree. Just look at it using just the array format. So this is basically to familiarize you guys with heaps, just so you can quickly recognize them. So grab something to write with, write a little happy face or an X or whatever.
Oh, no, we did this at A. The last one. Yeah.
It can't be just like 4. The children are 4, 7.
Oh.
They always have to be
But duplicate is.
Number 2 also.
Can the child be the same value as or
Is
does
it
it always
sure?
have to be less?
No, it can be the same.
Oh, also like.
Yeah, same is fine, right? Same or less, or same or more, depending on what kind of heap you're working with.
Question 2. All the arrays have an even number of nodes.
Yep.
Then it wouldn't be complete, right?
So, good question. Right, Lucas is saying that these aren't complete because they have an even number of nodes. You're close, right? You're thinking about a different term, right? Not complete. They are complete, but they aren't what? Full, right? Full means max nodes. Complete means max nodes on every level except the bottom level, and the bottom level is all shoved over. Right? So, for example, like B, like E, right? So C is full and complete. D is not full or complete. The example at the top is just complete but not full.
So it's E and C are right.
So on number 1, E and C, we like it?
Wait, E and C.
I heard E and C.
No.
No, it's just
Just C.
E is the
I heard C for sure. E. Why don't we like E?
Yeah, you just explained it. It can be complete but not full.
Right. It does not need to be full. Complete's okay. Right. E's good. What's wrong with A?
It's not
7
E.
is larger than
Yeah, 7's in the wrong spot here. What's wrong with B?
7.
Yeah, 77.
What is B?
No, it's just not.
It's just a binary. Full.
It's a binary search tree. It is full as well, but it's a binary search tree, right? So everything on the left is less, everything on the right is greater, right? What's wrong with D?
It's not complete.
Not complete. What's wrong with F?
It's a binary. Too complete.
Not a binary tree, right? It needs to be a binary tree.
Wait,
Why is D not complete?
why is D not?
Because if the last row isn't filled, it all has to be as left like possible.
Yep. On to the back. Which ones we like? Actually, I'll just call on people. Caleb, you like number 1? Haven't done it yet?
Yeah, I haven't done it yet.
Cool. Take 30 seconds, maybe 40 seconds. If you are done, move on. Look at heap down, and then we'll talk about it.
These two is one of the one.
Right. You could have like 17, 1, 2 over here. Right, the 85's there. Yeah. Yo. So we're making a max index. Which one's the largest? Well, B is currently at the top. Is B the largest? Well, isn't the largest in all heap? Really? Oh, it's QI. What is the largest?
Since like the start of the I don't get it.
No. Those are charts. Yeah.
If I got 55.
We good on number 2?
Number 2, yeah.
Cool. Number 2A, Chloe. We like it or no? Why not?
Because if you like look at which values go below each value, you find that 55 or 6 is not fit. It's bigger.
Right. 66's kids are like that, right? And we know just by looking at that, that's no good. Right. Number 2, Bob.
Yes.
Yes. We like it? Sure. Whoa. What the heck? Sorry. I don't know how to make this side thing go away.
Click on the papers.
That?
Yeah.
Oh, that. Sweet. Number 3, Devin.
No.
Why not?
Because one second. Because 3's child is bigger than 3.
Right. Totally, right?
That is bigger than 3.
Totally. Right? So, no. And number 4, Caleb. You said yeah. We like it? Sure. Totally. All right. There are 2 main operations. Heap down, heap up. Generally speaking, the big picture goal of these things is to take something that is almost a heap and turn it back into a heap. All right, so we can see on the right over here in this picture, you'll note that these are chars, right? In a char, large characters come at the end, small characters come at the beginning, right? So everything in here is a max heap except for the root, right? This is what we need. These are the preconditions in order to actually call a heap down. So in an almost heap, only the root is wrong. All right, so we are in that scenario. And basically what our heap down function does is it turns it from an almost heap back into a heap. Right? So when we're done, what should be at the top? Yeah, I agree, the largest, right? E. Now, E is a child of B right now. Is it definite that the largest value in our almost heap, where both kids are heaps, is it definite that the thing that's going to go to the top is one of these 2 kids?
No.
Yes.
Yes.
Is it no or yes?
It's yes.
Why is it yes?
Because everything below the second children, or what is it, second level,
Yep.
Must be lesser than.
Right, because it's a max heap. Right? So we only need to look at these 2 things. Right? So we take the larger one and we swap it. Which one's the larger one in this scenario? Sorry? E. All right. Cool. Now we got B. So this becomes E. This becomes B. Right? Then we call it again, or we keep our loop going. Right? Which kid do we swap with this time?
D.
D. All right. So that becomes D. That becomes B.
Oh.
Right? Do we need to swap anymore? No. Right? They're the same. Right? So boom, boom. There's our heap down. Yes, sir.
So is it recursive, and then each time you just pass in the new node as the root?
You can write it recursively or iteratively. Right? So if it's iterative, you basically just keep going until you're at the bottom, or you're bigger than your kids. If it's recursive, you just recur until that's your base case, right? Same thing. It could be either one, right? It works well both ways.
So like why don't number 3 was scheduled? Like you only check it when you swap it with like
So if you swap, then you keep going.
if you don't
If you don't swap, then you're already in a heap.
okay, so inserting a new
So again, just to recap, right? This scenario is the top node is wrong, and both of the kids are already in a heap.
okay.
Yeah. So I think we already traced this one correctly, hopefully. Cool. What I'd like you to do, and again, this one is the header for the recursive version. what I'd like you to do is try to actually code heap down. And by that I mean write it out handwritten. Right? Take 10 minutes. Right? This is an array of doubles. Yes, by hand. Think about it. What base cases do you have?
It's not working.
We have it extended to.
Sorry, no, we're working with just an array of doubles.
So we don't have tree methods like that.
You don't have tree methods. You don't need them, right? Remember, this is kind of like number 2 here.
There's already a swap method, right?
There's already a swap method.
It's like the position, the array position.
Wait, oh, you
Yeah,
always,
it's
so
not
you always
correct.
leave the 0 array open so that you can again
So it's well case.
There's actually not a good reason for it.
Oh.
I should probably change it for next year.
But then you have to make it weird. Like,
It would be 2k minus 1 and 2k's, I think.
Yeah.
No, but 2K would still be 0.
0, it would be
2K would be 0.
It'd be 2k plus 1 minus 1 and 2k plus 1. Like 2 times, I think it would be
Was 0
2
to just be K plus 1, K plus 2.
into k plus 1.
Wait for no way.
So it's 2k plus 1 and 2k plus 1.
Oh.
SAS.
Right, because 1's kids are 2 and 3.
Yeah. Oh, but then it'll be
No,
weird.
1's kids are 3 and 4. That's right.
It'll be weird. Because then you start at 0 to
So it'll be 0 would be 1, 2. 1 would be 3 and 4. 2 would be 6. Yeah, it would work. There's no good reason for it.
2K plus 1. Oh, so it's 2K plus 2, 2K plus.
Again, we're writing a recursive solution here.
Recursive.
Recursive solution, recursive solution. That's why we got k as an argument.
I see.
Mr. Owen,
Yeah.
what happens if the very parent of the whole thing is the same as this child? Is that fine?
So, look, if this was D, D, D.
If that was what we
Well, in this scenario, that wouldn't happen unless these would also smaller. But let's say this was E. Fine. Right. So it's
if that's E, it just stays.
if it's E, it just stays.
Make sure it's before the light Is it small? Just say small. Not? So such
No, because I just.
So
This one is not. Just swap until you just have to type this one. So you have a long broken letter.
Oh, I see.
The rest is complete.
Right.
So you want this to be the biggest number. So you want to check, is it bigger than this one, is it bigger than this one? If it was bigger than this one, which is D is bigger than D, you swap.
if it has two kids, you swap with the larger kid.
And then you check again, this is D bigger than D, D bigger than C, D is bigger than But then like, they are smaller than both, right? But then like, this is D is bigger than C, so you swap the largest.
Cool. And the only thing you forgot is
Because D is bigger than C, so you don't have to swap again.
what happens if K is out of bounds?
There's no swap. There's the swap.
And then this isn't a this is an array called.
Is in the array? Yeah.
So what if it's yours needs to compare with both yours. So if it's bigger, if it's smaller than both, which one should it swap with? What if this is a G?
And then we have to separate
All right, take another minute or two.
How do you start?
So just fix the value.
Is there a thing called 4?
Yeah.
We're accounting for the fact that the value is like, it might not be the smallest. Like if it reaches a point where it like fits there.
Correct. Then it should stop.
With the method stop by itself if all your if method doesn't exist.
If your code, if it doesn't enter an if statement, it just does nothing.
But like if the first if statement works, but unless like these two doesn't work. Like he's keeps
So if it goes in here and it doesn't enter any of these, then
Then
it
stop.
just keeps going. Then it just it does nothing.
okay.
No, it's okay. I basically have to do or like shift stuff.
All right, let's go over it.
I can narrate it.
So our first base case has to do with size.
K is
So if K
Smaller.
greater than or equal to size, return. Right, we're done. Sorry? It's a void method. Right, so we just return. Right, that'll just quit our void method.
I
If you didn't know that, that is a thing. Yep. Cool. So at this point, K's in range. How many kids does K have? Potentially 2. Might it have 1? When would it have 1?
If there's only 2 levels.
If there's only 2 levels,
Or if it's the last level.
or if it's like, what about this scenario here?
Like this, if it's the second to last level looking at the last level.
So, how do we know if we're in this case here? Check if 2K plus 1 is out of range. So, 1 kid. If 2K equals size, right? Then we need to figure out, do we want to swap? So, if array K is less than array 2K, swap array K 2K, right?
Why is it equal, not smaller?
Well, if it was equal, we don't need to swap. They're the same.
I mean, like 2K in size. Like, why is it equal to size smaller?
I'm going to code 2 kids down here. 2 kids. So else, oh, this is actually wrong. Sorry, I just got rid of this equal sign here. This is wrong. That shouldn't have been there, right? This is if K is greater than size, then we're bad. We're done. Oh no, actually that's fine. I take it back. That should be there. Yeah. So if 2K is equal to size, then we're on that level. Otherwise, we definitely have 2 kids, right? So we need to figure out which one's larger. So we'll do int larger equals 2K if array 2K is less than array 2K plus 1, then larger plus plus. Sure, right? So larger is now this one. Right, then if array K less than array larger, then swap array K larger, and then we need to recur as well. So what's the method called? Heap down array larger size. Do we need to recur in this scenario? No, because we'll be at the bottom in that scenario. Right? Boom, boom. There's your heap down. Right? Does that kind of make sense? Cool. Let's talk about when the heck would we actually use this. Right? So, heaps are used for 2 things. Yeah, it's actually like selection sort. So, heaps are used for 2 things. Heap sort, which we'll talk about now, and priority queues. So heap sort. Ready? This is basically improved selection sorts. Right? Can somebody recap how does selection sort work? Caleb. Beautiful. Find the largest, put it at the end. Do that a bunch of times. Great. How is a heap helpful for that? Largest is at the top. So we swap first And last, right, call heap down. Boom, boom. There's heap sort. You literally just do that a bunch of times. Right? So coming back to our arguments up here, right, size just decreases by 1 each time because that's what gets locked in. Right? That's it. Very, very easy. Right? So I think heap sort is like 3 lines maybe. Right? We got a for loop. Right? Swap first and last. Call heap down. That's it. Do we want to watch a video? Sweet. Ready? This is, in my opinion, the greatest dancing video of all time. Better than everything, Bob. Heap sort dancing. This is the best. It's even got a great soundtrack. Alright, we'll talk through it. So the first thing they're going to do is they're going to jumble up. This girl's killing it. I actually skipped. Alright, cool. So they're successfully jumbled, right? 8, 3, 4, 1, something, something, right? They're successfully jumbled. Are they in a heap right now? No. So the first thing we have to do is actually turn them into a heap. Now, this is the sneakiest part of heap sort. Ready? So what does heap down do again? It puts no, that is a heap. It takes, what's the precondition for a heap sort? For a heap down?
Everything below it is
The kids are heaps, right? So where are there heaps in this thing? At the end, right? Is that a heap by itself?
Yes.
Is that a heap by itself? Yeah. It doesn't matter. It's a single element, right? Because it doesn't have any kids, right? Remember, we're at the end of the array, right? Where's the first element that has a kid? Where? 2? No, 2 does not have any kids.
8 has
Who are his kids? His kids are these 2. Who are his kids? These 2. His kids are these 2. Her kids are these 2. His kids right here. Right? So all we do is we call heap down on him, right? Because his kids are heaps. Right? That will turn this thing into a heap. Then we call heap down on her. Her kids are heaps, so it turns her into a heap. Then we call heap down on him. His kids are already heaps because we've done everything else already. So all you do is just loop back to front, call heap down on every element. Sorry? Or the end, doesn't matter. Right? Because you can start at the end. Right? So that's what's going to happen first. What happened to the sound? Oh no. This is tragic. Wait. What happened to the sound? Thank you. Perfect timing. Shoot, what the heck happened to the sound?
maybe you mute it from
I hear it. I hear a buzzing sound. Hold on, let me turn off AirPlay.